Hello, everyone. Welcome back to SAT Math Question of the Day. We try to give approaches on both studying for the Math SAT and actually approaches on doing Math SAT problems. So we have the Brothers Chaiken here, falling over ourselves doing problems live. We haven't seen these problems before purposely. Seth Chaiken is PhD in from MIT and a professor emeritus in SUNY Albany in computer science. I'm Joel. I have a PhD in mechanical engineering. And we are ready to go. So how to approach studying for the Math SAT. A great way to do it is to sign up or do the Khan Academy courses. You just Google Khan Academy SAT practice, and you will have two options: a non-digital SAT practice course and a digital SAT practice course. Take the one that you think you will be taking. Take the appropriate course for you. The digital SAT starts in the United States for high school students in the winter of 2024. So we are now going to, so what we do is we do one problem a day. We only do the advanced questions with the presumption that if we show you we offer approaches on how to do the advanced questions, those approaches can be used for the medium and the foundations questions, but you should do them all. Okay, so we are up to here today. We are just cycling through these things. Last week, and today is Friday, but we didn't do yesterday, and we try to not miss Throwback Thursday. So today we will do a Throwback Thursday question from a test that was maybe from 20 years ago, and you will see the difference between the types of questions. Okay. We did that one on Wednesday. So we did that one Wednesday. We're going to skip quiz 2. Quadratic and exponential word problems. We haven't done a word problem in a while. So let's do this unit. Quadratic and exponential word problems advanced. Practice. We wait for the let's go little thingy, and then we will go let's go. Okay, come on. Okay, here we go. Let's go. Please look at the problem, read it, pause the video, come back, and we will do it. We will offer approaches on how to do it. Okay. Can we make this a little bigger? Oh yeah, look at that. Oh, that's nice. That's nice. Okay, here we go. An accountant for a certain state models the sales tax revenue that the state has earned over several years. The model shows that the sales tax revenue grew by 15% per year until 2 years ago, when it started to grow by a certain amount per year. Notice they underline the word million, which means that we have to be careful about that. If the sales tax revenue 2 years ago was $1.2 billion, approximately how much lower is the sales tax revenue this year than it would be if it had continued growing by 15% a year? So the first thing that strikes me in this problem is this is not a problem that can be answered in 3 seconds or 4 seconds. This is the type of problem you want to race. It's because of these types of problems that you want to race through the problems that you know how to do in 3 or 4 seconds, so you have time to digest this monster. Okay, whoa. The model shows the sales tax revenue grew by until 2 years ago. Hold on. Annotate. Until 2 years ago. So now where are we starting? Until 2 years ago. Okay, so it's like an English thing. Does that matter? Okay, it grew until 2 years ago. So before, let's put some numbers in this thing, okay? Let's say this is 1998. If the sales tax revenue 2 years ago in 1998 was $2.1 billion, now it grew by 15% per year. So this is 15% per year. And then after, it's 179 million. Or how about if we do it 0.1795 billion? No. Yeah, okay, 0.1795 billion. I just converted million to billion. Okay. Now, if the sales tax revenue 2 years ago was $2.1 billion, so now these are consistent. Approximately how much
Is
lower?
it Let me put in the decimal point really
Yeah,
clearly.
yeah. Okay, now, if the sales tax revenue 2 years ago was 2.1 billion, we got that modeled. Approximately how much lower is the sales tax revenue this year? Oh, this year. So this year is 2000, right? Than it would be if it had continued growing by 15%. Oh, okay. So they just want you to compare. 2.1 raised 15% twice. 2.1, 1.15 squared versus 2.1 plus 2 times 0.1795. Right? That's right. Is that right? That's what they
Yeah.
want you to compare. So what we could do is when we're done like doing it, we'll go over how we got. We'll go over approaches to how we knew this. Okay, how we got these things. So now it's a word problem. You want to really make sure you got this right. It's nice having a little picture of time, isn't it? The little timer. If the sales tax revenue was 2.1 billion. Oh, it says that 2 years ago, right? 1998 was 2.1 billion. And how much lower is the sales tax revenue this year? This year. Okay, this year. So that means this is the higher. This lower. It's lower. It's lower. It's lower. It's lower. Right? How much lower? So this should we expect this to be lower? Right? So should we put the numbers in with a calculator? Calculator. I have to use the big TI-84, I guess. Such a big calculator. Okay, so it's 2.1 times 1.15 times 1.15. 2.1 times 1.15 times 1.15 is 2.77. 2.77. Those numbers are pretty far apart from each other, but still, let's do it. 2.1 plus 2 times 0.1795 is 2.459. It is indeed lower. You should find the difference between the two, and it is 0.311. So that would mean B, right?
Yeah.
Yeah. Yeah. Okay. So it will be B. What do you think, Seth? You've been uncharacteristically quiet through this.
Yeah, well, it's okay. It's okay. It's just, when it's better to do it a bit more neatly.
Yeah. Yeah. Well. Yeah. I mean,
Uh,
You're right. You're right. You're right.
uh,
Yeah. So what do you think of the time? I like the timeline. Diagrams are very useful in word problems.
uh,
That's not it. That's
I think this the scribbling out and the uh, yeah, yeah. I want maybe you should try to express it more clearly so it's clear the difference between no between expressing add 2 times point one
right.
seven nine
Yes, we're going to go
five
over that in detail.
versus multiply twice
Right.
uh up by 15%.
Yeah, we're going to go over that in detail. Yeah,
Yeah.
I said
Okay.
when we did it, we are going to go back and actually
Yeah.
show how
And
to do
then when you
calculation.
write two numbers
Yeah.
that you're going to compute a difference of,
Right.
don't indent.
No,
Write
I wrote
2.77. Then underneath it, write 4. Write
right.
2.
Yeah, 2.4.
And let's use let's erase it. Let's neat. And then, in columns, do it in columns.
Yeah.
Underneath
Right.
2 point, yes, it's 2.77, and make the 7 and the 2 distinct.
Yeah.
Really clear. And then
Right.
underneath 2.459. 5, 9.
Right, right. I mean,
Yeah.
more intuitively, I like the verses because the verses really tells you what you're doing with these numbers. See the word
Uh,
verses. You're comparing two numbers. You're comparing two numbers, and to compare, and there are two ways to compare two numbers. You can make the ratio of the numbers, or you could do the difference of the numbers. But yes, in this case, and then you want the minus because you want to know how much lower, what is the difference in the numbers, not the ratio of the numbers, the difference in the numbers. Yeah,
yeah. They want how much lower is
yeah,
the revenue?
right. So
Yeah.
should we go back and slowly go over how you get those two? So if you first have to understand what, and a word problem, you have to, the main approach is you have to understand what's going on. If you don't understand what's going on, then just skip the word problem. Maybe in this situation, there's a long word problem. You have to really understand what's going on, just skip it. You have to understand, okay, so what's going on is that 2 years ago, the tax revenue started going up by $175 million per year. And that's what started in 1998. They want to know what it is in 2000. So if it starts at 2.1 billion here 2 years ago, and it goes up by 1.79 million per year, then that it really is 2.1, and then after the first year, it's 0.1795 because we have to be consistent with the units because they underlined the units to remind you. And then you have to add another one, 0.1795, and that's the money based on this thing. So we can change color.
So that is the money that is the money that the problem says was actually obtained.
That's right.
It started to grow by that constant amount each year for 2 years.
That's right. That's right. So that's
The 15% is what it did before.
yes, exactly.
And now they ask, in an imaginary situation where instead of growing the way it really did, what if it grew at the same old rate?
Exactly.
Okay.
That's right.
Then
So you have to know
how much lower would it be if it had
that's right.
continued to grow by the fictional amount?
This is a hard problem to understand. And did you notice, like, when I did it, I spent a lot of time trying to understand what the problem was. In fact, the problem like this, you may want to spend more time understanding it than actually doing the calculation. But yes, you do have to have some knowledge about how to make things grow by a percent. Either like a percent and then grow by another percent. You have to understand percent. You have to understand how to make things grow by a percent.
Well, people who make a lot of money by working with money have paid lots of attention to understanding stuff like this written in words.
Okay, fine. That's irrelevant because we're talking about high school.
Well, it's relevant because a lot of people, I'm sure a lot of people who are listening to us, what they want to do in the future is make a lot of money by working in business and finance.
That's very good. So they rather than right this second in their time in life right now, you have to know how to do relatively straightforward percent.
Well, they would also why not use the time of life right now to get ready for something that enables you to fulfill your wishes.
Absolutely. So
not just to get a good score in the SAT.
That's right. So basically, but you have to understand what to do first. We have to grow. We have to grow 2.1 by 15% per year for 2 years. That is the mathematical problem. We have to grow a number 2.1 We have to raise it by 15% to get the number in 1999, and then we have to take that number and raise it again to 15% to get to the number 2000. So I don't know if people have watched before, but I love the shopping formula. The shopping formula is when you want something to you have to, percent growth. The new number is the old or the original number times 1 plus, now it's growing, so it's 1 plus die called D, the decimal of the percent. The decimal of the percent. So in this case, 15% is 0.15. So in 1999, the old number is 2.1, the original number is 2.1, and it multiplied by 1.15. So that's the number 1999. Now, we have to get the number 2000. So that's 2.1. We take this number, which is the 1999 number, 1.15, and then we multiply again by 1.15, because this is now the new number. This is now the original number. This is now the original number going from 1999 to 2000. So these are the two numbers you have, and I simplified it to 1.15 squared. And that's it. And I simplified this. 0.1795 plus 0.1795 was 2 times 0.1795. But there are different ways to do the percent growth. You could actually take 15% of 2.1 and then add it to 2.1. So if you're not sure how to do percent growth, there's go back to the, well, I think there's a percent unit here, or just go back to your textbook and review percent growth.
Or let's see, so we'll also see the explanation they give in a few minutes.
Yes, very good point. Very good point. So do you have another explanation on how to do the percent growth problem?
No.
Okay. So we think it's that answer, so we'll do it. That's right. We better move on because we have Throwback Thursday to do, and we have a whopper one today, I think. So I think we thought the answer was, we expect this. Let's give it a shot. Wow. Okay.
They agree with us.
This is so inconsistent, right? Now let's see how we answer. Sometimes we see that, sometimes we don't. What are you going to do? 8 steps. You see that? It's a dead giveaway that this is not a short problem. No. What are they doing with this 2.1000000? Are they crazy? What is that? What is this? What is this? And they can go like that? I don't understand. Oh my God. The answer looks more intimidating than the question. The sales tax revenue is now growing by a fixed amount each year, so we can model it using a linear equation. We forgot to say the word linear. Oh, we're bad. Okay, fine.
Well, we
forgot to use the word linear. Guilty.
I think we did it in a direct, appropriate, efficient way.
Yes, we did. I was thinking linear, but I forgot to say. Okay, we will use the, okay, fine, is the initial amount. The rate of change is this. Let's be careful about our place value. Place value? What about units? Can't you just make it simpler to say units? Anyway, revenue is that plus that. Oh, are they really expect people to carry all those zeros around, waste their valuable time in the SAT writing all those zeros? My God. Wow. My goodness. Okay, anyway, please consider what we did, which is to convert the millions to billions. But if you're not sure what to do, then just do it this way. Now they're bringing in the exponential equation. Oh, so you have to know that percent growth is also exponential growth. That takes an extra step of understanding, which is good to have.
Well, your shopping formula is, well, so it's exponential growth in one period.
Right. Yes, it's exponential.
Right. So exponential growth is repeated growth by an excess or discount that's frequently expressed in shopping, but instead of the growth happening once, it happens n times.
Yeah.
and the n is the exponential, is the exponent, and 1 plus the percentage of growth it's 1 plus what you call d. 1
Right.
plus d is the exponent.
Right. Right. So you can see that there are different approaches. I took one approach to explain it. They took a whole different approach. Not
Yeah.
bad, but they took another approach. It's good to try to actually understand both approaches. They do this thing. They go directly to the exponential growth model. It'd be better if they wrote that B was 1 plus D. Right? They don't really say that. They say it here, but in more general form for
No,
exponential growth.
it's not M, wouldn't that be? Oh, B, yeah, B, yeah,
And
the B.
D is the
B is
decimal
the
of
base. Okay, B is the
and
base.
D
Yeah,
is the decimal of the percent.
yeah, yeah.
Here they just sort of explain it here. The
Yeah.
15%, then each year was 1.1. That's just very confusing. I know, personally, that's a little confusing. But that's the derivation of this.
Yeah.
Um,
Yeah, I've criticized this. Their explanation is too long-winded.
yes. The shopping formula is really the good thing to do, but you have to do it what's known as recursively. You do it 1 year, then you do another year, then you do another year. But in general, it's the shopping formula applied to multiple years is the original
Yeah,
times
yeah,
1 plus d to the
yeah.
n, where the n of the number of periods that you compound, the n of the number of periods.
I think there's another. Please. Oh, never. Yeah, yeah. If you shift it, the annotation will get messed up.
N
I
is the
think
number
an inconsiderate thing they did in the explanation
yeah.
is they use the general symbols M. They use M. They used X for the number of years
Right.
during which the growth occurred.
Yeah.
And then they used M and B for the constants in linear growth. And then they used A and B for the constants in exponential growth. They should not have used the same
wait.
B.
Let's just take a break there.
Because the two B's, the same letter, in paragraph 1 mean different from what the B means in paragraph 2.
Seth, but there's red B and blue B.
Yeah.
Red B and blue B, okay? There's red B and blue B. But the X...
red B and blue B.
But the X is the same. The X is the same. The X is the
number
of years.
That's why it leads to confusion because you would see that the X's are the same, but the B used in the first formula is a different meaning from the B in the second formula.
No, but it's red B.
Even though they used a different color.
They used a different color. It's a different thing. It's a different. I'm gonna say, look, it's a different thing. Plus, they also defined it. They said B is the starting amount.
Of course, they defined it.
And
yeah. So, however, in reading, writing, and talking about math, unfortunately, it does happen that the same symbol, the same letter, is reused to mean different things.
I feel a pet peeve coming on.
The same is often in all levels of mathematics.
Yeah.
The writer will use the same letter for multiple purposes.
Yeah.
Within the same document.
And then they go on and they say the former. It's so confusing. The former.
Yeah.
The former and the latter. I mean, your brain was already fried on the SAT, and then you're thinking about the former and the latter. I really like the approach of the year. Put some years in so that you don't have to think about the former. Certainly for someone like me who gets my left and right, my plus and minus confused. Okay. Anyway, so that's it. Okay. So now we'll move on to Throwback Thursday, which is was supposed to be yesterday, but we didn't meet yesterday. So we have a question from the old days before the 2016 test, where you had to do some more reasoning other than just knowing what you have to know, just knowing stuff from school. So here we have our Throwback Thursday question. It looks like a little bit of number theory here. Anyway, please read it. Come back to us, and this should be Seth's specialty because he has the PhD in that. If n is greater than 1 and each of the three integers n plus 2 and n plus 4 is a prime number. Oh my god. Oh my god. You'll never see this in a modern test. Then the set of set of three. Oh, when Seth says, "Oh, it's not good," then the set of three such numbers is called a prime triple. Oh wow! So we get an education on this question. What? How many different? How? Wait, there are how many different? Oh my goodness, Seth. I would skip this. Okay, if I was actually taking the test, I would skip this problem. Wow.
Yeah.
Wait, but there's got to be an intelligent way to do this,
let's
right?
see. Are there prime triple? There's 3, 5, and 7.
Well, Seth's using brute force.
Yeah, so there's at least one.
Okay. Too bad we don't have to have that. Too bad we don't have the answer on how they did this. The book only has the answer. We're gonna have to get the book out. So there's 3, 5, and 7. So let's see if there's another one. Wait. So n would be 5. 5, 7, and 9.
Well,
let's play with it, right?
7, 9, 11. Okay. So okay, I think yeah, I think I could I could explain why there's only one triple.
Okay. Yeah, it seems to be that way.
I'll tell you why. I'll tell you why there's only one triple. A triple, let's call a triple of numbers. A triple of numbers is a triple of numbers in the context of this problem is what they say.
Right.
It's 3 numbers that are spaced 2 apart.
Right.
Okay, now let's say let's look at an rather arbitrary looking triple of numbers. You know, like not necessarily 37? Prime.
How about
20? That's a 20, 22, and 24.
Right.
Now, if you divide them by 3, what is the remainder? The remainder is 2. The remainder, when you divide 22 by 3, well, you divide 22 into 3 parts.
Yeah, it's 1. The remainder is
right.
1.
Hold on. So you get the 3 parts from the 18. That's how you get 3 parts from the 18 and a remainder of 2. And then you add 2 more. So it's like getting a remainder of 4. But you could have put the extra 3 in the 4 into the quotient. So you divide by 3 of 22, you get a remainder of 1.
Right.
Similarly, add 2. You could get the remainder divided by 24 by adding. So basically, you get from one remainder to the other by adding 3 and then reduce.
Right. Okay.
Okay. So if you add, for example, here you get 2 plus 3, and then 2 plus 3. 2 plus 3 is 5. Remainder is 2. Add 3. You get 5. No. What am I trying
Your
to say?
remainder goes down from 2 to 1 to 0.
2 plus 3 is 5. And
So just the
no,
remainder goes
yeah.
down.
I'm sorry. We're not adding 3. We're adding 2.
Yeah.
Okay. When you go from one number to the next, we could get the remainder when dividing by 3 by adding 2 to the old remainder, and then reducing by 3. So you get 2 plus 2 is 4. Reduce by 3, get 1. Follow the same rule. 1 plus 2 equals 3. The remainder of 3 is 0.
Yeah, the remainder
So the pattern of remainders by dividing by 3 of a triple always has the pattern of 0, a 1, and a 2.
Right. Okay.
So among any 3 numbers in a triple, one of them is divisible by 3.
Uh-huh.
And so if the one divisible by 3 is not 3 itself, one of the 3 numbers cannot be a prime.
Got it.
And so this is the only triple for which all 3 numbers are prime, and pick the answer.
Wow, that was a really smart way of doing it. You're saying
it's the kind of thing that would be a neat problem, not too hard if you're studying the beginning, elementary number theory.
Right. Unfortunately, most people taking the SAT,
relative to the modern curriculum of our educational state of 2023, this is a hard problem.
Right, because number theory is not stressed.
That's because they're not people don't teach as much interesting and deeper intellectual things today they used to teach.
Right. Yeah.
That's why we're doing Throwback Thursday.
Right. Good. Yeah. Okay. Yeah, so I don't think we need to check the answer in the back of the book. I think it's pretty clear. Seth made a solid explanation. By the way, when I said I would skip this problem, I really should have said skip it and come back to it if I had time.
Okay. So when you however, writing out examples was a really good idea.
Yeah.
Did you reach this? So what conclusion did you reach when you wrote out those 7 examples?
I didn't reach a conclusion because when I got to this point, Seth said, "Oh, I know how to do it," and I said, "Okay, Seth, then you do it." And I never finished. You should have let me struggle with it a little more, like most.
Yeah, I should have. Yeah, notice. So let's see. Of the triples you wrote out, underline. Look at the pattern.
Yes.
The multiples of 3 are these 9s, and then we have the 15s.
Right. Yeah.
And you skipped. You didn't do. You didn't do 15, of course, because 15 is a prime.
Right.
But if you did the next triple,
no, 15 is an odd. 15.
I know. If 15 is a prime, it's not a prime. But if you wrote underneath this 15,
right. Yeah.
What happens?
It's like a little pattern. Yeah, it goes.
Yeah, leave it that 15. 17, 19, like notice the 15 is in the pattern, and it's not a prime.
Yeah, the numbers go like this, see?
Yeah. So the idea is instead of looking at any pattern, see the prime numbers, the pattern formed by the prime numbers is very, very mysterious.
Yeah.
However, the pattern that does emerge, the pattern that is relevant, is the pattern for all triples all triples, not all prime triples. And the pattern for all triples is the one that Joel wrote.
Yeah. So
Yeah,
probably
where this is, this is a triple, and this is a triple for the next. Yeah, this is the triple for the triple for the obtained by taking the first triple and adding two, then add another two, so forth. Well, you could also think of triples of all numbers like adding one. In which case the ones divisible by 3 will have the pattern. Let's say start with 0. Let's start with n is greater than 1. So you start with 2. 2, 3, 4. Then add 1. 3, 4, 5. And then add 1. 4, 5, 6. I'm underlying the ones divisible by 3. Then 5, 6, 7.
Right. Damn. Okay.
And then let's continue it a few times.
Okay.
Then let's see, 6, 7, 8.
Yeah.
And then 7, 8, 9. Let's see, 8, 9,
Okay,
10.
so
I'll do two more.
It's fine.
9,
We're done.
10, 11.
Okay.
See the pattern there.
Yeah.
Blah, blah, blah.
The point before,
Blah, 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 and blah, blah, blah.
But here's something interesting. This can't possibly be true. Right here, all of these numbers are prime. The other two numbers that are not prime are prime, like 5, 7 are prime, 7, 11 are prime.
Okay, well...
Now, but when you get high enough, that can't possibly be right. You can't, if you pick the first number...
yeah.
Prime.
Well, that's part of the mystery. Part of the mystery is the pattern. Part of the mystery is the pattern of what's called twin primes, pairs of prime numbers that are separated by 2.
Yeah, but there has got to be prime numbers are never. If you keep going, like, what's the next prime above 37? Are you saying that if you pick a prime number,
okay,
it's a number 2, 1, or 2?
It's, if you look up, you could get a lot of information about mathematics from Wikipedia. And Wikipedia quotes the following, and I'm going to read it carefully.
Okay.
So twin primes are primes like 3, 5.
Yeah.
That differ by 2. 5, 7.
Okay.
Is a twin prime.
Right.
7, 9. Well, 9 isn't a prime.
Right.
11, 13 is the next twin prime.
Got it.
13, 15. Well, 15 isn't prime.
Right.
17, 19. That's a twin prime.
Okay.
23, 25. 25 isn't. 20, 27, 29, 27 isn't. 31, 33 isn't. Okay. Go on and on. Right. However, if you could read about the context in Wikipedia, it says in the state of mathematics today, it is unknown whether there are infinitely many twin primes.
Wow. Well, first of all, I just answered my own question. I wanted to find a case where you have a situation where there's more than one, where only one of these 3 is a prime, and I found one. Thank you, Seth.
Of course, it's if more than one being a prime means that you have twin primes.
Right. Yeah.
And the only triple in which there are 2 twin primes is the one where the first 2 are twins and the second 2 are twins, which are 3, 5, 7.
Right.
So mathematicians conjecture the best guess but without really knowing it, is that there are infinitely many twin primes. It's called the
Wow.
twin primes conjecture. In
Wow.
other words, mathematicians have never discovered a proof. They do not have any proof that there's a limit. They're only that the pairs of that there are only finitely many twin primes.
Wow. So you take a ridiculous prime number, like it's not probably not prime, but like 27,965,792,000,000
Yeah.
da 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 75 plus one and plus two. Wow, those are big numbers. Okay. There's a project for someone who no, seriously, there's a project for someone who wants to major in math and get a PhD in, or even more, become even more famous.
Yeah.
To solve that problem.
So yeah. So what's kind of interesting is that the twin primes question is very, very difficult.
I can imagine.
Mathematicians have still not resolved the answer to the question about how many twin primes there are.
Right. Okay. Yeah.
But if you go just one step above, triples of primes, the answer is this question on the SAT, which is very easy.
Yeah. So just you tweak one little thing in the world. Well, mathematics models the world. You tweak just one little thing in the world, you have drastically different results.
You go from 1 to 2,
Yeah.
one pair of primes separated by 2, and then another pair.
Wow.
It changes the question from unknown solution, very challenging, has not been solved, to all right, pretty easy.
So maybe next time we have relatively difficult problems like this, you should let me suffer as an 11th grader would suffer. Rather than blow us all out with the brilliant number theory question, which is probably above most levels and most people.
Yeah.
Okay, lesson to be learned. Okay, but the important thing was the previous question, the word problem. Take it slow on the word problems. Okay, everyone, I hope you enjoyed today. I hope you got something out of both the first part and this interesting. This is a really good pre-2016 question. You'll never see a question like this on the modern tests, digital or non-digital. Okay, everyone, have a great day. Have a great weekend. We'll hope to see you next week. And like us, dislike us, give us comments on YouTube videos. And if you have any SAT math questions, email them to us at SATmathQuestionOfTheDay at, it's at gmail.com. Okay, everyone, have a great day.